Hi, Mr. Unkert here with example number 1 of experimental probability. So, in the experimental probability assignment, you're probably going to get a question similar to this. This question starts off with stating that the table below shows the number of touchdowns scored per game of the first 8 football games Windham High School plays. So you see the first game they scored 1, the second game they scored 3 touchdowns, 1 touchdown, 2 touchdowns, 2 touchdowns, 1 touchdown, and then 3 touchdowns. Okay, so the question reads, based on this data, what is a reasonable estimate that WHS scores 3 touchdowns in their next game? So we have to consider the GBT technique. So G stands for the number of good outcomes. So that's the number of times that Windham High School scores 3 touchdowns, because that's what we're looking for. So you see in the second game, the third game, and the 8th game, they scored 3 touchdowns. So that was 3 total times they scored 3 touchdowns. The number of bad outcomes is the number of times they didn't score 3 touchdowns. So that would be the first game, the 4th game, the 5th game, 6th game, and 7th game. So that would be 5 times they did not score 3 touchdowns. And then the total number of outcomes is the total times they played in this particular instance. So that would be 8 games. So really, to figure out this problem, you need to look at the good and the total outcomes. And the probability that they score 3 touchdowns in the next game let's just say 3 in either the next game. And since I'm running out of room, I'm just going to abbreviate this next. So 3 in the next game, the probability of that is going to be the number of good outcomes over the total. So it's going to equal the number of good outcomes over the total. So it's going to equal, there are 3 good outcomes over the total outcomes, which are 8 total outcomes. Okay? You can also represent this in a decimal form. So if you divide 3 by 8 on your calculator, you're going to get it in decimal form, which is 0. Point 3 7 5. So the probability is 3/8 or 0.375 as a decimal. And you can just put 3 divided by 8 in your calculator and you would get this probability. So that includes example 1 in experimental probability. Okay, on to example 2. The following data summarizes the number of deer Timmy sees on his morning walk. This shows deers seen, so each dot represents a day that you see that number of deers. So let's say we asked a question on how many days did you see 5 or less, or how many days did Timmy see 5 or less deers? Okay. So more than 5 deers, you can consider this a couple different ways. So more than 5 deers could be considered the good outcome if you're thinking more is better. So that would be 1, 2, 3, 4, 5, 6 days that he saw more than 5 deers. And therefore, then the bad outcomes would be 5 or less. So that would be 1, 2, 3, 4, 5. And the total outcomes would be 11. Okay, so if we were phrasing it this way, we'd do bad over the total. Or we could think of it as a good outcome is what they're asking, which is 5 or less. So that would be 5 days he saw 5 or less. The bad would be the days he saw more than 5. That would be 6 days. And the total would stay the same, which would be 11. So it depends on how you phrase it, but in this case, we'd be looking for good over the total. Either way, the probability of 5 or less is going to equal the amount of times he saw 5 or less, which is 5 times, over the total, which is 11, which, if you put that in decimal form, it's 0.5 repeating, and if you round to do 2 decimal places, it's going to be 0.56. Okay, on to example 3 in experimental probability. The following table shows the number of likes Billy got on his last 12 Instagram posts. So you got 4 here, 22 here, 0 here, 45 here, 0 here, 12 here, 1 here, 17 here, 93 on this one, 0 on this one, 0 on this one, and 26 on the last one. Based on this data, what is a reasonable estimate that Billy's next post to Instagram gets 0 likes? Well, you'd think 0 likes on social media is a bad outcome, but in this case, I'm just going to focus on the good outcomes and the total outcomes, and I'm going to consider that 0 likes is a good outcome. Okay, so let's count the number of times he gets 0 likes. So that's 1, 2, 3, and 4. The total number of outcomes is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. The probability that he gets 0 likes on his next post is going to be the number of good outcomes. In this case, a good outcome is considered 0 likes over the total outcomes. So it's going to be 4 over 12, which simplifies to 1 over 3, or as a decimal rounded to 2 places is 0.33. Okay, on to example 4 of experimental probability. Let's take a look at this one. The following chart shows the number of points Margaret scored in each volleyball game this season. Based on this data, what is a reasonable estimate of the probability Margaret scores 12 to 15 points in her next volleyball game? Okay, so we can see that the good outcomes are 12 to 15 points. And we can see, looking across, that she did that in 4 different games. So That's an outcome of 4. Now we have to figure out the total number of games. So we have 4 games for 0 to 3 points, plus 1 game for 4 to 7 points, plus 3 games for 8 to 11 points, plus 4 games for 12 to 15 points, plus 2 games for 16 to 18 points. So that's 6, 9, 10, 14. So the total number of outcomes is 14. So our probability of 12 to 14, or 12 to 15 points, rather, is going to be 4 over 14, which is going to equal 2 over 7. Let's take out a calculator. Okay, 2 divided by 7 equals 0.285. I'm going to round that to 2 decimal places and write 0.29. So you may see the answer as 2/7 or 0.29 if it's rounded to 2 decimal places. Okay, on to example 5 in experimental probability. 1,450 out of 2,250 voters vote for candidate A. 676 voters out of 2,250 voters vote for candidate B. What is the probability that the next voter votes for neither candidate A or B? Okay, so we have to figure out of these 2,250 voters, how many didn't vote for A or B. That's going to be our good outcomes. So to do that, let me not do that. Let me add those. So 1,450 plus 676. Let's add them. So we get 6. We get 2,126 voters that voted for either A or B. So that means that we're going to subtract that amount from the total voters to find out who didn't vote for A or B. Okay. That's going to be our good outcomes. So I'm going to borrow from the 5, cross it out, make it 4. And we have 10 minus 6 is 4. 4 minus 2 is 2. And then 2 minus 1 is 1. 2 minus 2 is 0. So we have 124 that didn't vote for either A or B. So that's 124. And the total outcomes we have so far is 2,250. So we'll say the probability of not A nor B, or neither A nor B, is going to equal the 124 that didn't vote for A or B out of 2,250. So we can simplify that. If we have this, we get 62 out of 1,125. And we can pull up our calculator. Let's clear everything. So 62 divided by 1,125. Rounding it to the nearest hundredths place is going to be 0.06. So 0.06. Okay, Mr. Unkert here, and after we've gone through some of the examples, you may also have to pick a answer that is written as a percent. So I have some probabilities here that are both written as decimals. Now, probabilities written as a decimal can run from 0 to 1, with 0 being the same as 0% chance of it happening, and 1 meaning that there's a 100% chance it will happen. Okay, so let's say I have two different probabilities of events occurring. So the probability of event A is 0.06. To change that to a decimal form, so I have to change it to a percent rather, I have 0.06. I'm going to move the decimal point 2 places to the right. So that would be 6%. Now the probability of event B is 0.23%. So to change 0.23 as a decimal, rather, to change it to a percent, I've got to move the decimal point 2 places to the right. So that is a 23% chance of that happening. Okay, I hope this video helps you with the experimental probability assignment. If you have questions, please email me or comment in the Google Classroom. And thank you for watching. Have a great day.